We're live. A very good evening to one and all present. On behalf of Team ISF, I welcome you all to day 2 of India's largest virtual science fest, India Science Month Online. ISMO is a month-long celebration of science and technology, and it is an initiative in bringing science closer to society. We are here to bring the voice of science closer to you and your homes. Our festival features a bunch of talks, workshops, panel discussions, demonstrations, online games, competitions, and more, all of which is scheduled on our website. And you can go over to our website and have a look at the entire program schedule. Register for whatever event you are interested in and make sure that you link it to your calendars, because we'll be sending you calendar updates for everything. Before we begin today's session, I would like to launch a quick poll to understand the audience that we have here today. So I request you all to please take out 30 seconds and give us answers to the polls that you will see on your screen. It's time for the second poll. So as you've all seen on your screens already, our audience is primarily consisting of college students, and most of our attendees don't have a very good idea of the topic at hand, but are eager to know more. And so I'm very, very happy to introduce our speaker for today. Allow me to welcome Professor Mark McCaughrean from the European Space Agency. Professor McCaughrean is the Senior Science Advisor in the Directorate of Science and Robotic Exploration. He has worked in the field of astronomy and space exploration in the UK, the US, Germany, and Netherlands. He is also working as an interdisciplinary scientist in the NASA ESA CSA James Webb Space Telescope. So, Professor, it is an absolute honor for us to have you as part of this session. Thank you so much for taking out the time to join us here.
Thank you very much. It's very kind of you to invite me to take part in the festival. It's a pity that it's online. I would love to have the opportunity to visit India again and give talks. I was there just a few years ago and gave talks across Well, it's an amazing country with lots of incredible people, and I was very privileged to travel there. But for today, we'll talk online, and I'm going to give a presentation about what the European Space Agency does. As you just mentioned, I'm the Senior Advisor for Science and Exploration, so I'm going to talk a little bit about space science, looking out through the universe into our solar system and beyond, but also about what we do with our astronauts and what we do with our robots throughout the solar system. I'm sitting at the moment in the Netherlands, which is where the European Space Agency has its big technical center, the place called ESTEC. Again, unfortunately, we're separated by many thousands of kilometers, most of us, but technology brings us together for this talk this afternoon. So with that, I will now share my screen and start the talk. So thank you very much, and look forward to questions at the end.
Right. Professor, as you begin sharing your screen, I'd just like to tell all our attendees that you are all free to put in your questions in the Q&A box, and Professor McCaughrean will be sharing his knowledge with us through the course of this session and will answer your queries at the very end. At the end of this entire session, a few space enthusiasts will get the opportunity to interact with Professor in a one-on-one interaction. And so those of you who are interested for the same, we request you to stick around till the end of the session. And with that, Professor, over to you.
Thank you very much. So let me just start by going back in history. This is now 2021, as we know, and that is 60 years since the first human flew into space, Yuri Gagarin, in April 1961. And then just a couple of years later, the first woman went into space, Valentina Tereshkova. And in the 60 years since then, we've come an enormous distance, to the point where we now have this amazing machine, the International Space Station, which is a flying laboratory in space. And in many ways, the most important thing about it is the word international. It's that it is a collaboration between the US Space Agency, NASA, the European Space Agency, the Russian Space Agency, Roscosmos, the Japanese Space Agency, JAXA, and the Canadian Space Agency. And the fact that over the years since 1961, the world has changed enormously from the Cold War, that we'll talk a little bit about today, to a world where we share and we collaborate and work together in space. And not only the people on the ISS, but also with India and with China and with Brazil and with other countries around the world. Space exploration is something which is a thing for all of humankind. It's the thing that we all do and we all do together. And hopefully today I can share some of the things that we're doing inside the European Space Agency. So let's take a quick look at one of the experiments that's been sitting on outside of the space station for quite a while. This is the Columbus module, which is the European Space Agency's laboratory inside that tin can that you see there. But on the outside, what you see in the presentation is an instrument called SOLAR, which until recently, until 2017, was monitoring the brightness of the sun as seen above the Earth's atmosphere. And you might think that's something we know very well, that the brightness of the sun and the spectrum of the sun, which you see in the picture in the lower left corner now, is something that we know very accurately, but actually we don't. It's very difficult to get an absolute calibration, a measurement of exactly the amount of energy arriving at the sun and how it changes over time as well, because the sun goes through various cycles. And I'll come back to that later in the talk. But the key thing about this measurement, measuring the absolute spectrum of the sun in actual physical units, is that it's a direct input into what we must model and work on when we look at climate change. So if we don't know the exact amount of energy arriving from the sun, it's very difficult to make very accurate models of how the climate is changing over time. So that's just one of the many experiments on the outside of the ISS. The inside, of course, unlike those first astronauts who were in spacesuits, flew up in space for a few hours and came back down in the same spacesuits, we can now have shirt sleeves environment where the astronauts, this is one of our astronauts, Samantha Cristoforetti, enjoying a view on the Earth through the cupola there. And inside the laboratory, there's Luca Parmitano, another ESA astronaut, working on experiments which use microgravity, the conditions on the space station in free fall as the space station orbits the Earth. There is effectively no gravity inside the space station. And so we can look at processes and phenomena which are very hard to study on the Earth. We can look at them in long duration spaceflight on the ISS. But in this little box, what we can actually do also is spin the inside of the box to create artificial gravity. And you would say, well, why would we want to do that? We've come into space to get away from gravity. Well, in this box, you can have simultaneously microgravity, no gravity effectively. Maybe you can simulate Mars gravity, moon gravity, and the Earth's gravity by spinning that central centrifuge at the different speed. Why would we do that? Well, this is one experiment which we've been doing on the space station, looking at how bacteria work under different levels of gravity, because those bacteria can actually be used to extract minerals from rocks. And we can use that on the Earth, what's called biomining, but maybe in the future we'll use that on the moon, use it on Mars. And so we need to understand how those different species of bacteria from the Earth work under different under different gravity conditions. And so that's just one of the many experiments which we're doing internally on the space station. And just in this short 30 minutes, I can't go into more detail today. But of course, the space station is very close to the Earth. And one place that we want to go back to now to explore further through the solar system is back to the moon. So the moon is, whereas the space station is 400 kilometers above the Earth's surface, the moon is 400,000 kilometers away, so 1,000 times further away. And it's not easy to get there. But of course, we've done it. We've sent human beings there before in the 1960s and the early 1970s. First astronauts from NASA went there. This is Buzz Aldrin on the first landing on the moon, Apollo 11 in July 1969. But in 1972, we stopped going to the moon. And the world has changed in many ways, as I said, since then, politically and technologically. And we are about to go back to the moon. And this time, Europe will be part of that journey. So this is the Orion crew vehicle, the next generation crew vehicle to go to the moon. The shiny part you see on the top there is NASA's crew vehicle. And the back part, the bottom part there, is the European service module, which provides the power, the water, the life support systems. And that is developed from one of our previous technologies, which went to the space station. And so we're going together to the moon. And when we get to the moon in the next few years, we'll start building this. This is called the Lunar Gateway. And this is a small version of the International Space Station, which will involve the same partners, the United States, Europe, Canada, Russia, and Japan, to build a small version of the space station for long duration visits above the moon, and also going down to the surface of the moon. Now, whether that will happen in 2024 or 2026 or 2028, but there are very good prospects that it will happen in this decade. And we have just started building components for this Lunar Gateway right now. Now, going back to the moon and just putting boots on the moon and coming back again, that's not what we're interested in. We're interested in a longer duration stay. One of the locations which is very interesting to us is to go to the south pole of the moon, which you see in this picture here. Now, why the South Pole? What's exciting about that? Well, some of the craters which you see in this image near the South Pole are permanently in shadow. They never see sunlight. And we know in those craters, there is water in the form of ice. And so by going to the South Pole of the moon, we can perhaps think about building a facility there, which would allow us to extract the ice from the dark shadowed regions and then turn that ice into water for drinking, into oxygen for breathing, and into hydrogen and oxygen for rocket fuel. So by going to the moon and extracting the ice there, we may be able to use this as a staging post for exploration further beyond. Now that's about humans and what it means to build human bases on the moon. But what's the real motivation for us as scientists? The moon is a record of how the solar system formed and evolved in the very earliest phases, 4.5 billion years ago. On the Earth, much of that evidence of the early evolution of the solar system has been erased through plate tectonics, through erosion, through water. So by going to the moon, a place which is much less altered, we still have important lessons to learn about this very earliest phase in the solar system when there was lots of material flying around, forming into planets. Now, one of the planets which is most intriguing to us is the planet closest to the sun, Mercury. Mercury is roughly just 1/3 of the distance that the Earth is from the sun. So it gets much more energy from the sun. It gets much hotter. It's up to 450 degrees centigrade on the sunlit side of Mercury. That's the same temperature as a pizza oven. So it's not a place that you want to go and stand on the surface as a human being. But we are sending spacecraft there. NASA has sent 2 spacecraft there in the past, and now Europe and Japan have sent a very large spacecraft there called Bepi Colombo. And here it is, just a few kilometers away from where I'm working when it was being tested in our giant acoustic chamber, a room which has huge speakers for blasting out the loud sound of a rocket launch to make sure the spacecraft can withstand that amount of vibration. There are 3 spacecraft here in a stack 6.5 meters high. A small Japanese spacecraft in the top behind that sun shield, a European spacecraft in the middle, and then a propulsion module at the bottom, which helps us get all the way to Mercury. Now, we launched in 2018, and to get to Mercury, we're not just going straight there. We're using flybys of the Earth and now Venus in order to change the trajectory of the spacecraft to get us accurately to Mercury. And just a couple of months ago, at the late 2020, Bepi Colombo had its first flyby at Venus. And I just want to play you briefly a short film showing Venus from Bepi Colombo with just a little bit of music to introduce the new year. That was the first of 2 flybys that Bepi Colombo will make at Venus. And another of our spacecraft, which we launched just at the beginning of 2020, is also doing a similar series of flybys. That's a mission called Solar Orbiter. Now, Solar Orbiter is a joint European-American spacecraft to go close to the sun to study the wind and the energy coming from the sun, flowing past the spacecraft, and then later on coming to the Earth. There's much we still don't understand about the sun, and this spacecraft, Solar Orbiter, will allow us to get much more detailed images and spectra and other analyses of the surface of the sun and the material coming from the sun. So I said it was launched just less than a year ago in February 2020 from the US, and earlier this last summer we actually published the first data showing the whole disk of the sun there at ultraviolet wavelengths. And then on the left-hand side and on the right-hand side, we're seeing these tiny little flares on the surface of the sun. Tiny by the standards of the sun, but actually as big as a continent on the Earth. And those flares have never been seen before. So this is one of the first science results. And they're important because they might be a way of providing energy to heat the atmosphere above the surface of the sun to millions of degrees. The sun itself is only a few thousand degrees, but the atmosphere is millions of degrees, and we still don't understand how the energy gets into what's called the corona of the sun. Now, as I said, Solar Orbiter is also using Venus, and this is a simulation of what happened just a week ago or so when Solar Orbiter flew over one of the poles of Venus, and both Bepi Colombo and Venus will be Solar Orbiter will be using Venus again this year in 2021, almost at the same time, just spaced by 2 days in August, flying again above the atmosphere of Venus to use the gravity to redirect the trajectory in order to get, in the case of Bepi Colombo, to Mercury, and with Solar Orbiter to be able to get closer to the sun and also lift up out of the plane of the solar system to look down at the sun on the North Pole and then at the South Pole as well. We've never done that. We've never taken pictures of the poles of the sun. Now, why is the sun interesting? Of course, it's not only interesting in itself, but the huge amount of energy released in solar flares can actually come towards the Earth, and this energy fills the solar system. The wind and the light fill the solar system, and they affect everything that goes on in the solar system. One of those impacts is something which hopefully some of you will have got to see last year, which is where you can form the tail of a comet. A comet is an icy ball a few kilometers across, and as the sun's light heats the surface of the comet up, the wind then blows it out into a tail. This is Comet Neowise, which we saw in July last year. And this is from where I live in the Netherlands, pictures I took at the beach there. So that was a beautiful sight to see, the first bright comet we've had for many years in the Northern Hemisphere. And when that energy arrives at the Earth, that energy then can also create the aurorae, the northern lights and the southern lights above the North Pole and the South Pole. And those aurorae are phenomena where energy hits the Earth's atmosphere and then causes molecules and elements in the atmosphere to glow into these beautiful colors. But the Earth isn't the only place that has an aurora. Aurorae are actually common across the whole solar system. You can take pictures of them at Jupiter and Saturn, and some of the other planets, we have evidence that there's an aurora there, and some of the moons. We can see evidence for glowing gas interacting with the solar wind. But one of the most unusual places we've seen recently is actually a comet, like Comet Neowise. But in this case, this is a comet which we flew very close to between 2014 and 2016. This is Comet 67P Churyumov-Gerasimenko, which the Rosetta spacecraft, European Space Agency's Rosetta spacecraft, arrived at in 2014. And this is one of the many beautiful images of that comet giving out gas and dust. Now, what we've recently discovered by looking through the data is that there is an aurora around the comet as well. Just a little bit of physics for you today. Most of this is just pictures, but a little bit of physics. How does that aurora actually form? Well, in this case, the comet, when it's heated up, gives out water molecules. And then you can have electrons coming from the sun. They get speeded up as they approach the comet and can break the water apart. In this case, one of the hydrogen atoms has been released and has got added energy. And when that atom decays, it loses the energy, it gives out a photon, and that photon is an ultraviolet photon, and that's an aurora. You can do the same thing with another electron coming in, being accelerated in the magnetic field of the comet, breaking the molecule apart, this time to release an oxygen atom, and gives it some energy. That energy is released. You get a different wavelength. Again, an aurora. So that's the first time we've discovered an aurora around a comet from the Rosetta mission. Now, Rosetta finished in 2016, but just before it did, we were looking for the little lander called Philae. Philae was landed on the surface in 2014. And in fact, we lost it. We didn't know exactly where it had landed. It returned data. We saw the surface of the comet, but we didn't know exactly the location it was at. And so in September 2016, we took some images just before the end of the mission. And this is a close-up image of the surface of the comet taken from the Rosetta spacecraft. And in this picture, we found Philae. So if I zoom in a little bit here, and then I turn up the brightness, now Philae is in this picture just on the right-hand side. So if I zoom in, there it is, hiding underneath an overhang on the comet. If I turn up brightness, there you are. So that's the little Philae lander, the size of a washing machine, sitting on a comet. And that, to me, again, is one of the most beautiful things about what we do in space exploration, is that that's a human-made machine which we built and we put onto a rocket and we sent into space. And then more than 10 years later, it arrived and landed on the surface of an object that's 4.5 billion years old. And we can take a picture of it. There it is. And it gives us some scientific data back as well. So for me, that's one of the most exciting journeys we've had in the European Space Agency, but there's much more to come. For example, in 2022, we're going to launch this mission called JUICE, which is going to Jupiter, and in particular is going to explore the moons of Jupiter, the big 4 moons, 3 of which have icy crusts. They're covered in water ice, maybe tens or even hundreds of kilometers thick, and beneath that water ice, we believe there is liquid water. So by exploring these moons in more detail, we're exploring environments where possibly there might be life buried deep underneath the icy crusts. So we're excited about JUICE going all the way back out to Jupiter. It will take a while. It takes 7 years to arrive at Jupiter. But the other reason we're excited is that Jupiter, of course, is a gas giant planet. It's the biggest planet in the solar system. But since the 1990s, we've discovered thousands of planets like Jupiter, like Uranus, like Neptune, and in some cases, maybe like the Earth, going around other stars. These are not real images, they're artist impressions of what those planets look like, but we're now able to study those planets in great detail. And the European Space Agency has a whole range of missions which are looking at the planets, exoplanets we call them, orbiting around other stars. And I'm just going to, I won't talk about the bottom two, which are missions in the future, which will be discovering new planets and studying their atmospheres, Plato and Ariel. But I'm going to talk a little bit about the ones at the top. So Chaos, in the top left corner, is a mission involving a very small satellite. There's the same acoustic chamber again, where you saw the giant Bepi-Colombo spacecraft. And now here's little Chaos. And Chaos was launched at the end of 2019 and sent into an Earth orbit. And it's studying planets around other stars by measuring in great detail how much the light of the star changes when the planet moves in front of it. It's what we call a transit. So the star gets a little bit fainter just for a few moments, for a few hours, as the planet moves in front of the star. And by measuring the drop in light, we can measure the radius of the planet, the size of the planet. And that helps us measure the density of the planet because we know the mass from other measurements. But let me show you a picture of the launch of that satellite from our French Guiana launch site in December 2019, a Soyuz rocket.
10, 9, 8, 7, 6, 5, 4, 3, 2, unité, temps de décollage.
Successfully launched and has been returning scientific data. This is an artist's impression of one of the first objects it studied in detail, a Jupiter-type planet, but very close to its parent star, so close that the planet is actually thousands of degrees in temperature. So it's certainly not a planet that you could ever live at. And in fact, it was christened in one of the newspaper articles, one of the worst planets in the universe. Well, I think maybe the Earth was one of the worst planets in the universe last year, but hopefully 2021, things will change for the better. Now, we're not only interested in planets, but also the stars themselves. So this is a picture taken from the ground at the European Very Large Telescope in Chile, in the Atacama Desert, showing the Milky Way. And since 2013, we've had a mission called Gaia, mapping the positions and distances and motions of more than 1 billion stars in our Milky Way extremely precisely. To give you an idea of just how precise, Gaia can measure the equivalent size, the equivalent width of a human hair seen at 2,000 kilometers distance. And with that level of precision, we can create data like this, which shows the motion of stars in the Milky Way, in this case, over 1.6 million years. So this is the whole sky spread out on just an ellipse here. So some of the motions seem to curve in crazy ways, but they're all straight lines effectively when seen on the sky. And that lets us make a movie of how Milky Way is changing with time. And we can run that movie backwards and try to work out how the Milky Way, our galaxy, how it was put together originally billions of years ago. One of the satellites which has also been studying the universe for many years is the Hubble Space Telescope, now more than 30 years old, a collaboration between NASA and the European Space Agency. And one very interesting recent result from last year involves Betelgeuse, a famous star in the constellation of Orion, the red star in the top left corner there. This is a picture again from my home taken last spring. Betelgeuse is a red supergiant. It's a huge star, far bigger than the sun at the center of our solar system. And it's so big that we can actually we can take pictures of it and see some structures on the surface. So here are pictures taken over time with different telescopes. Something strange happened in 2019 is that Betelgeuse got fainter, and it we know it gets brighter and fainter as it oscillates and pulsates, but it got much fainter than it had ever been before. Now, the reason that these stars get faint sometimes is because they don't look like the sun again. They have these enormous convection cells, material rising up to the surface and falling down again. So this is a simulation of what these stars look like. Now, we didn't know why Betelgeuse got very faint. It's possible that it was just these convection cells. Maybe it was about to explode in a supernova. That's what some people thought or even hoped for. The other thing which was possible, that material was being ejected from the star and covering the star up. And Hubble took fantastic data, and in fact, that's what it found. It found that material had been expelled from the surface of the star as gas. As it moved further away, it cooled down and turned into dust. And when you see it from the Earth on the right-hand side there, that blocked a part of Betelgeuse from the Earth's view and made it fainter for a while. So it's recovered now. It's mostly the same brightness, but still very interesting. We know it will explode in the future. Will it happen whilst we have the opportunity to watch it? Who knows? Maybe. Now, Hubble, as I said, is 30 years old, and it's a relatively small telescope with a mirror 2.5 meters in size. So we've been working with NASA and with Canada on a new telescope called the James Webb Space Telescope. We've been working on that. I've been involved since 1998, so a very long time. And this is a much bigger telescope, which will collect much fainter light from the distant universe. And while you see here in this picture that it's just an artist's impression, the real telescope looks like this. This is the real machine. You see the people on those cherry pickers there. So this is a huge telescope with a giant sun shield, which all has to be folded up to get inside a rocket launcher, which is a European launcher, the Ariane 5. And hopefully on 31st of October, on Halloween this year, we will launch the James Webb Space Telescope on its journey. And for me, I've been involved because I'm very interested in the birth of stars and planets. So if you look here, this is a visible wavelength view of the Orion Nebula, the famous place where stars are being born. But if you go to the infrared, which is where the James Webb Space Telescope works, you pass the dust and the gas and you see thousands of young stars in this region, all crammed into a very small volume. And those stars are just 1 million years old, so much younger than our sun. And in many cases, there are planets being born around those young stars. So we'll be using the James Webb to go and study those objects in much more detail. Other people will be using it to look at exoplanets, to take images of exoplanets going around other stars, to measure their atmospheres. And then many people will be using the James Webb Space Telescope to look at the distant universe, to look at galaxies across the sky. And as you look further and further away from the Earth, you look at further and further back in time, you see that the galaxies change. They get redder because of the redshift, the stretching of the space-time, if you like. And because the objects get redder, there's a point deep in the past where we can't see them at visible wavelengths anymore with Hubble. You need to go to the infrared. So to see the most distant and youngest objects in the universe, you need the James Webb Space Telescope. So that's one of the main reasons that we're building it. But at ESA, we're also building a telescope to look not at the visible and infrared light coming from galaxies, but to look at the dark matter and dark energy, which makes up most of the universe. 1/4 of the matter of the universe is actually dark matter. We don't see it glowing. And much of the energy in 1/4 of the it's much more than the baryonic, what we call the baryonic matter, the normal matter, but 1/4 of the mass energy in the universe is dark matter. And the rest is dark energy, which is also making the universe stretch and expand quicker than we thought. So we're building the Euclid mission to explore that, to measure dark energy and dark matter. And in the center of many of the galaxies which you see forming in the supercomputer simulation, there will be black holes. And so we're building big new observatories to study material just before it enters the black hole, heated up into X-rays, the Athena Observatory. And we're measuring gravitational waves as black holes join together and merge and give out these waves, these pulses through space-time, the LISA Gravitational Wave Observatory. So let me just finish by coming back into the solar system and come back to Mars, because that's another place which we're interested to explore. Why is Mars exciting to us? Well, Mars today is cold and dry, has very little atmosphere, but we know that billions of years ago, it had lots of water. It was warmer and had a thicker atmosphere. Now, how do we know that? Well, our Mars Express spacecraft, which has been in orbit since 2003, sees evidence for water on the surface. So these are the giant volcanoes in the Tarsus region, the biggest of which is Olympus Mons, the biggest volcano in the solar system. And if you look away from the center to the right, there's a giant landslide down from the side of the mountain. And we know by measuring the parameters of that landslide, we believe that it took place underwater, that the landslide collapsed into a liquid ocean. We know that there's water under the surface of Mars today. By using radar, we can penetrate more than 1 kilometer beneath the surface of the South Pole. And when we do that, we look in this region here, we see reflections in the radar. We see that it's water reflecting the radar beam back up into the sky. The strange thing is that that is at less than temperatures of around 200 degrees Kelvin, so minus 70 degrees or so Celsius. And how is that possible? How is that water liquid? It's not because of the pressure, it's because it's full of salt. And salt lowers the freezing point of the water so far that it can still be liquid at these very cold temperatures underneath. Now, of course, Mars is a place where lots of missions launched last year. The UAE's mission HOPE was launched from Japan. The Chinese mission launched with its rover, and NASA's Perseverance mission launched with its next rover. And that's an interesting location for us. So here is a series of images showing the place where the Perseverance rover is going to land, in a place called Jezero Crater. Jezero is interesting because it's again a region that we know in the past had liquid water and had volcanic activity. Something like this billions of years ago. This is a volcano on the Earth today, but Mars looked like this billions of years ago. If we zoom in, this is the place where the Perseverance rover is going to land. It's a river delta, a place where water has flowed out and created this beautiful delta. If we tip it on its side, you can see how that river delta is raised above the crater. And the reason it's exciting for us in Europe is because Perseverance is going to be collecting samples, which then in a few years' time, we will go with NASA, pick those samples up and bring them back to Earth. So this is the beginning of what we call Mars sample return. Between then and now, we'll be launching in 2022 the European Exomars rover, working with the Russians in this case. And the Exomars rover, which is named for Rosalind Franklin, involved in the discovery of DNA, is to look for evidence of life under the surface of Mars. The surface layers are sterilized by ultraviolet light and radiation from the sun, but 2 meters down, there's enough protection that there could still be life, either in the past, maybe even today, on Mars. We already have a mission at Mars, which has been studying the atmosphere since 2016, the ExoMars Trace Gas Orbiter. It's been taking fantastic images. Here's another river delta, for example, showing again there was liquid water on Mars. But the great thing we've been looking for at Mars is methane. Methane is a rare gas. It's only there in very small amounts, we think. But if it's there today, something's making it. And it could be life that's making methane, like on the Earth. Crazy thing is that even though we've been looking for methane, other satellites, other missions have seen it, but our machine, our new satellite, the TGO, which is much more sensitive, hasn't seen it at all. It doesn't find methane. And one possibility is that, in fact, what people were seeing as methane before might just be carbon dioxide, the most common gas, with absorption lines in the spectrum here, which nobody had ever calculated before. So we're still looking, still trying to see if there's methane on Mars, but it's a very exciting area for people working in space science. Is there methane on Mars? And if there is, what's making it? Could it be life? One place there is methane, just to finish off, there is methane on the Earth. And we study at the European Space Agency not only the distant universe, but we also have a very strong program of studying the Earth's climate, the Earth's atmosphere, the oceans, the ice. And methane during the lockdown last year, in many countries due to coronavirus, methane started increasing. And that methane was coming from human-made locations. So in one case here, we see it coming from a gas well in the United States. That gas well was probably not capped properly, and there was excess methane coming. And from a factory in China, methane was seen coming out. So for all that we spend a lot of time and effort in the European Space Agency looking out to explore the universe, it's also very important that all of you watching, all of you engaged, realize that there is no place for us to go. This is the planet which we were born on. This is the planet we live on. There is no planet B. So for all that we look out into the universe and explore, we have to remember that we have to preserve the planet we live on and now and make sure that it's livable for future generations. So this is a picture of the layers of the Earth's atmosphere. This very thin layer that we all live in is something we need to preserve. Now, one thing, I'm just going to finish now with a short film, and that film shows you something that we at ESA do, which is to engage with the public, and we'd love to bring it to India in the future. We call it Space Rocks. It's where we get astronauts and scientists to talk to artists and musicians and writers and other people in culture to bring things together to make people aware of the universe, but also protecting the planet Earth. So let me just show you a quick film, and then we'll go to the question and answers. This is the event we held in London in 2018, just to give you a feel for what Space Rocks is like.
Hi, I'm Dallas Campbell, and welcome to Space Rocks.
Beneath you is groaning and creaking, cryogenic fuel is boiling off, and then you get the word from your Russian instructor, we're off.
This is a galaxy cluster forming right there.
And we're very, very lucky to have the project scientist of Rosetta with us here. Please welcome Matt Taylor!
I'm a local lad, born in London, so it's nice to come back here and talk to people and say, you too can go to European Space Agency.
It's been brilliant. The reaction from the audience has been wonderful. The questions have been great. I've learned an awful lot.
Nice to meet you. You can have the Earth.
Brian May's been here, one of my own heroes.
How cool is this? Thank you so much.
Right, thanks very much.
Too.
I've really loved it.
And during lockdown, of course, we haven't been able to have big physical events like that, but we do have an online stream where we talk to interesting people, musicians, astronauts, artists, scientists, engineers. Please, if you want to follow along, come and watch us. We do a show every week called Uplink. So have a Google for Space Rocks Uplink. You'll find our YouTube channel, just like the one you're watching now. So thank you very much for listening. And I'm looking forward to your questions. Shukriya.
Thank you so much, sir. That was a wonderful session, and we have had a surplus of questions in our Q&A box. And I mean, I can see that the audience is absolutely thrilled by this session, and there was so much information. I think the images that you used were absolutely beautiful, and they really captivated all of us. So I'm gonna just hop on to a couple of questions that our audience wanted to ask you. The first one, a very interesting one. Personally, are there any books or resources on space exploration that have interested you and that you would recommend for people to go through?
Wow, well, that's a good question. Of course, there are many. There were books which I read when I was a kid, long time ago. And of course, most of those are actually out of date in some way, because what we've learned in space exploration during my lifetime has been astonishing. It would be very difficult to know where to start, to be honest. There are hundreds of books out there, and lots of them are being written by young astronomers and young space scientists now. So it's something perhaps we can talk about offline. I would need to put them together. But there are lots of, as I say, young people writing amazing books about exoplanets, about the history of the universe in the future. What's going to become of the universe in billions of years' time, not in billions of years in the past. So yeah, it's a very rich literature. And in fact, as a joke, I actually think I'm the only astronomer so far that hasn't written a book. So maybe I should join in, or maybe I should not write a book. But no, there's a lot of fantastic books out there. So I suggest that if you have a Google around, or go on Twitter, you'll often find lots of people talking about very good, interesting books there.
Sounds good. Well, if you do write a book, I'm sure the Indian audience here is looking forward to it. So the next question would be, so space exploration, there are a lot of government agencies such as NASA, ESA, ISRO, that are doing a lot of work in space exploration. Do you see any upcoming collaborations which are going to yield massive results, or which will, have a very historic change in the way we've been looking at space exploration? So could you tell us a little about collaborations that perhaps you have planned with NASA, ISRO, and so on?
Yeah. Well, look, everything that we do in ESA is collaborative. We have 22 countries. That's what we are. We are collaborative from the ground up, but we also collaborate more widely. Probably, actually, ESA collaborates with more space agencies than any other. There are political reasons that NASA doesn't collaborate with China, for example, but we do. And so we have a new mission called SMILE, which is to measure the Earth's magnetosphere, the bubble around the Earth, the magnetic bubble, and how it interacts with the sun. That's with China. We have had missions in the past with ISRO. We've been involved in various missions there, and we will be in the future. We're in constant dialogue with ISRO. And of course, the Indian space program has very exciting things going on. I mean, having your own Mars orbiter, I think, is a remarkable achievement. And there are areas where we're working with smaller countries outside of Europe, trying to help them in some ways to yield expertise from what our experience has been. With NASA, we do an enormous amount with NASA all the time. And we, of course, have the James Webb Space Telescope, which is coming up, which is personally very exciting. But we're always looking at new missions with NASA. There tend to be very common collaboration. Space science, but also the exploration missions, of course, with the astronauts, and Earth observation. So recently we launched a mission called Sentinel-6, which is an Earth observation mission shared with NASA and with Russia as well. So yeah, I mean, collaboratively, we're always open to that. It's our DNA. Our DNA is to collaborate between countries.
That sounds lovely, sir. I'm sure all of our attendees are looking forward to hearing more about upcoming collaborations between ESA and ISRO in particular, which is obviously doing very well in terms of space exploration. And I think we will ask you one more question before we move on to the meeting room where you will be interacting with a couple of attendees. So my last question is, we received a lot of comments regarding the James Webb Telescope that you touched upon in your talk. So on a personal note, would you have any big prediction on what the James Webb Telescope can tell us in the coming future? What is your personal take on this thing?
Well, I have personal hopes, and the hope is that, when I got involved in 1998, we had started finding objects in star-forming regions like Orion, which were not stars. They weren't heavy enough. They didn't have enough mass to fuse hydrogen and helium in the center, to fuse hydrogen into helium to make it glow. These are objects called brown dwarfs. So these objects are formed at the same time as stars, but they never start fusing hydrogen. Now, we know that those objects get very small. They can be even as small as Jupiter, but we don't know what the smallest object is that can form in the same way as the star. So for me personally, I'm going to be looking for those very, very small objects, which will tell us something about how stars are born in a general sense. And then also looking for planets forming around those stars. So that's, for me, those are the things I'm interested in. But, you know, and there are many topics to do with distant galaxies, to do with exoplanets, to do with the way that galaxies evolve over time. But the great thing about JWST is that even though we've been building it for a long time, and I see one of the questions, why is it delayed? It's incredibly complicated. The technology involved in JWST is astonishing and difficult. So yes, it's late, but you know, when it flies, it still will be by far the most powerful facility of its kind. But the great thing is that it's not focused on one topic. It's not saying, I'm going to answer this question. It's a general purpose observatory. And anybody watching now or in the near future, you can apply to use the James Webb Space Telescope. Even if you're not from ESA or from NASA, the world can apply for it. And you can, of course, you have to be good and you have to write a very compelling proposal. You have to say why you want time. But if there's a problem you think you want to solve in astronomy, write an application and you can use the observatory. So that's the great thing. It's not, we don't know the most amazing things it will find. We'll only know in 20 years' time. So everybody online here can be part of the big discoveries from James Webb, because it's the unexpected things which are always the most exciting. We know it will do amazing things, but it's the unexpected things which I think everybody should be looking forward to. When we find them, we'll let you know.
On that note, that was a wonderful answer. Thank you so much, Professor. Again, we will be hosting a very small meeting room where Professor McCaughrean will interact with a couple of enthusiasts who wish to ask him a couple of questions. And any last words for our audience before we end the session, sir?
Well, again, thank you very much for inviting me. Again, we know we're living through crazy times at the moment around the world. Europe is, you know, nobody's sorted out this coronavirus yet, and so it's a pity that we can't all be in a room together sharing these things. Because I love to take the question and answers personally and talk to people. That's the thing I miss the most, is not being able to travel and meet people around the world. The last time I was in India, it was a fantastic experience for me. So I hope we can do this again in the future. So I hope everybody stays well and safe and healthy in 2021. And look forward to October, when we will launch the James Webb Space Telescope. And it'll take us a few months to make everything work properly. The pictures won't come the next day, but let's see what we get back from JWST. And let's see what we can do together between India and Europe. I look forward to it. Thank you very much.
Thank you so much, sir. It was an absolute pleasure having you at the festival. We really are very grateful for the time that you've taken out to explain everything that the ESA is up to and is going to be up to. And again, we would tell all our attendees now that we will be posting a link in the next 5 minutes in this webinar chat. We have very limited spots in the session coming up. So please make sure that your questions are brief, that the kind of interaction that you want with the professor is streamlined and absolutely calm and not very haphazard. So we will just be ending the webinar soon. And you all can expect to see Professor McCaughrean in the meeting room now. You are more than welcome to head over to our website and check out the coming festival program that is lined up for the coming few weeks. We have a lot of events all across the month of January. The events are back-to-back, really fun, and the weekends are going to be very, very busy, and there's something to do for all, because we truly believe in making science available to all. So that brings me to the end of this session. Thank you so much for joining us, and keep celebrating science with us, and keep listening to the voice of science. Thank you so much.